Welcome to the 23rd lecture for Physics 4B, and the last lecture on electromagnetism for a while. In this lecture, we look at applications of Faraday's law, including inductors. The first application we will look at is the AC transformer, which shows how, through Faraday's law, AC voltage can be easily stepped up or stepped down with a very simple device. Then, we spend most of the time in the lecture looking at inductors, as well as electromagnetic energy stored in the magnetic fields of inductors. Inductors are the last of the linear circuit elements we introduce in this class. With these circuit elements, that is, inductors, resistors, and capacitors, we will soon look at the time-dependent circuit and AC circuit. We will return to the full electromagnetism in the last week of the semester to complete the Maxwell's equations and work through a striking consequence of the four Maxwell's equations. What I was hoping to do today was go through two more applications of Faraday's law. The first is application to a transformer. I don't know, how many people have seen a device that looks like this? I feel like many people don't see it until you start doing experiments. It's called a variac. It's a variable power voltage supply. So your power outlet only gives you 110, 120 volts. This, with this dial of the knob here, it can provide up to, I guess, 140 volts. I haven't tried it, but I kind of trust it though. Or you can turn down and provide much less voltage of 30 volts. Or, you know, I think I can actually set this up to demonstrate that it works. The best way to do it would be with a light bulb. Because there's some kind of relationship between how much voltage you're applying and how bright a light bulb is, right? So I don't know. I haven't actually tried it. It's very possible that this will not work, but we'll see. So right now on high, is it on? Okay, it's not on. Let me try turning this on. Is it on yet? Is it on yet? Still not on? Still not on? Oh, wait. Did I turn on this thing? Okay, I didn't turn on this thing. All right. Okay, it shouldn't be on right now. Is it on yet? Okay, very dimly on, right? It's saying it's putting out 30 volts. Let me double the voltage to 60 volts. Still on? Yeah, brighter. And yeah, I won't go too high. I guess I can go up to 110. So this is a transformer. And so let me actually pass this around. And what you will see is that it's a very simple device. It has no moving parts other than this knob that I'm turning. It has no sophisticated electronics. All it really is what you see here. Two pieces of wire that's wound around the core, a Faraday core. And, you know, so let me pass it around. This is the variac or voltage transformer. And it's a simple device because the principle on which it works is this simple single principle of Faraday's law. So let me draw the picture of this. I guess this is a 5-to-1 transformer that I will quickly do the demo of. So I should have titled this correctly. So let me call it mutual inductance and AC transformer. I almost thought about skipping mutual inductance altogether because in my experience dealing with the circuit, mutual inductance doesn't come up that often. But I realized it does come up in one circumstance. That's the circumstance of an AC transformer. So let me draw a giant picture of this ferrite core, except I'll make it rectangular so that it's easier to draw. So I have this ferrite core. And remember what we talked about this ferrite core. It serves one main function. One main function is that it has magnetic permeability that's higher, so that you send in a small amount of current that makes the magnetic field inside the material bigger. Okay? So the way an AC transformer is made can be this way. So I have one loop that's winding around this one side of this core. Oops. Let me just dot. And for the one that I'm going to demonstrate with, it has 50 turns. So let me just say there are 50 turns here. All right? And this will generate magnetic field, right? It'll generate magnetic field that kind of goes this way. This would be my field lines for magnetic field. And this ferrite core actually serves one other role. If I was doing this out in space, then once the magnetic field goes outside of this material, it should look like a dipole field, right? Going all over the place. But when you have a ferrite core like this, these field lines, they kind of get trapped inside. So they don't actually go out anywhere. The field lines will sort of just bend around the material and close on it itself like this. So in some sense, it makes your transformer more efficient because you're not losing any of these field lines that you generated by sending current. All right, and somehow this device is being used to generate voltage or different voltage. So if you wanted the same voltage, so you're applying some amount of voltage here at this end, you apply some amount of voltage V in. And if you wanted the same voltage, then you wouldn't bother going through this device. You just connect something as parallel to it, and you'll get the same voltage. So with a transformer, you want a different voltage for some reason. You might want a lower voltage, or you can actually get a higher voltage. This variac, so you plug into 110 volts, but it claims it can give you 140 volts. So you could sometimes get higher volts. We'll see that in demonstration in a bit. So to get a different voltage out, what you do is you wrap a different coil of wire over here. So you so this is the second set of coil winding that's in that variac. So you wrap a different set of wires here. Let me try to wrap it in the same direction. So viewed from top, it should go counterclockwise. Okay. For the one that you are going to see in demo, there's a total of 10 turns here. And let me just get this wire out here. Okay, wire out here. And you are looking at, okay, how much voltage is coming out? Okay. So let's just see if we can figure out how this thing works. Why should you get voltage out here if you apply a voltage here? So let's say, let's first figure out what doesn't work. Let's say we hook this up to a battery. We hook this up to a battery, providing some steady voltage difference of V naught across this, from one end of the wire to the other end of the wire. All right, what happens then? You have a coil of wire with a voltage applied to it. What do you imagine happening to it? Yeah, there's current flowing through it. There's magnetic field induced. All right, I guess let's say that much. Okay, so there's some current flowing through it. And in fact, if we think of this like a solenoid, then we can even figure out what this magnetic field is. Although, let's not think of it like a solenoid. Let's think of it like a toroid. Wait, toroid? No, let me do solenoid. If you think of it like a solenoid, then what this magnetic field will be, it should be mu naught, the loop density, or the number of loops per length times the amount of current that's flowing through. Right? All right, so you have the magnetic field. What happens then? Yeah. So we want to see if this magnetic field will induce a current here. Let's say we are applying a steady voltage. So at some time soon, we get a steady current. So with the steady current, we get a steady magnetic field. Will that lead to a voltage being induced on this set of coils? Yeah, this is the important thing to note. Faraday's law depends on the magnetic flux changing. It could be changing due to some geometry changing. It's turning, so that changes the flux. Or it could be changing because the magnetic field itself is changing. But however it happens, the magnetic flux has to be changing. So if we have steady current, that will not happen. So as you are going from zero current to this current, something might happen here. After that, it's gone. Nothing else happens here anymore. So that means we actually have to step back a little bit and first to figure out what kind of voltage we have to apply here so that we can actually get some voltage output here that depends on this. So so this is what we want to do. In this region here, we want to have some, especially through this area, we want to have some non-zero change of magnetic field. That's what we want to do. Or non-zero change of magnetic flux. You can see that nothing in the geometry will change as a function of time. So that means we have to change the magnetic field somehow. We have to make the magnetic field going through here a function of time. How would you do that? Yeah. So this is where AC comes in. So far we haven't dealt with the AC or alternating current, right? We only dealt with where we are applying a DC or direct current or so unchanging, constant voltage. It's when dealing with the Faraday's law, things get more interesting when your current changes as a function of time. So that means your applied voltage will also have to change as a function of time. So this is what I'm going to imagine hooking up at this end. Instead of battery, it will be an AC current source. I actually have one hiding under here. We'll be using this as part of the demo. This is my, most of you have seen this function generator, right? It generates a voltage signal that can change as a function of time. So this is the symbol that usually stands for it. So let me call this voltage as a function of time. And just for sake of completeness, I'm going to call it this. Voltage as a function of time is equal to some amplitude times cosine of omega t. Some sinusoidal wave. Doesn't have to be sinusoidal, but sinusoidal is actually the simplest one we can deal with. Okay, that means the current that's being passed through will be a function of time. That means the magnetic field here also will be a function of time. So current is a function of time. Nothing else here depends on the time. So magnetic field is a function of time the same way the current is. So because of this, when you go this far, the magnetic field here is a function of time. So this rate of change of magnetic flux will be non-zero. All right, so I guess this is what I want. I think if this is my applied V in, then I think I will get some output voltage here, V out. That's going to be a, that's going to be a function of time. And more importantly, it'll depend on my applied input voltage and some bunch of other parameters. And I want to figure out, okay, so what is the relationship? If I have 50 turns on one, so some number of turns N in, and I have some 10 turns or some number of turns N out, how will this voltage compare to the voltage here? Will it be higher amount of voltage or lower amount of voltage? Higher? All right, let's see. I guess so this is the way your textbook does it. I think the first time I saw it done that way, I didn't like it, but it is the simplest way to get at this formula. So, the reason I didn't, so if you read Giancolli, this is how Giancolli does it. The reason I didn't like it the first time I read it was I like to think in a sequential linear order. So I like to start out with the voltage I'm applying, current I'm getting, and then move in the sequence. The way Giancolli does it, he starts out with the magnetic field that's inside the Faraday core. So, but I think that is actually the simplest place to start, even though it's non-linear. So let me start from there. Let's say you have some amount of magnetic field, and you have this magnetic field as a function of time, right? And what I want to do is, given this magnetic field, what is the induced voltage around this coil? What is the induced voltage around this coil? Let's treat this end first. It's a little bit easier. So let's say something is generating this time-varying magnetic field. So at this end, I want to figure out what is my voltage output. So I want to say, all right, so my output voltage, V out here, as a function of time, it will be given by Faraday's law, right? So induced voltage will be equal to, I'm just going to deal with the magnitude. So it will be magnitude of the rate of change of the magnetic flux. Here, how do you think magnetic flux depends on the magnetic field? Let's say this cross-section has area A. So what should be the expression for magnetic flux? I mean, it should have magnetic field in there somewhere, right? So, I want you to think back to the basic definition that magnetic flux is defined as, well, magnetic field times some area element, and you integrate it over the area of some surface that you are considering. Right? That's what you're doing every single time. Sometimes it gets really simple. Sometimes it gets a little bit more complicated. This is actually a shape that that's potentially more complicated, at least conceptually. Let me write down the formula for magnetic flux in this case and see if it makes sense. So a lot of you might start out with this. Magnetic flux here is the magnitude of magnetic field times this area that I shaded. It doesn't actually stop there. It's this thing times the number of turns and out. Does this make intuitive sense? That the magnetic flux around this loop is the magnetic flux through a single loop times the number of loops you have. Yeah. If it makes intuitive sense to you, then great. You can stop it there. The next thing that I might consider is it's for people who keep questioning, how does that work? I guess this is the way that made sense to me, so I'll explain it this way. So the area that the path is enclosing is a little bit actually complicated looking. So if it's a single loop like this, then the area is a circle, right? If you have multiple loops, then the area that it's enclosing it has a quite complicated shape. But what is true is that as the magnetic field goes through, it goes through this portion of the area, and then it goes through another area in the same direction again. So it's like a field line crossing this one single continuous area multiple times in the same direction over and over. And that's what results in this. But either way you understand it is fine. I think the easiest is, well, single loop is this. I have more than one loop, so I have to multiply it by this to get the total magnetic flux. Okay? So that's an expression for the magnetic flux. With that, I can write down what is the rate of change, the time derivative of this, and get some sort of expression for V out. So let me just go through that. So this is equal to N out and A constants. Okay, so they get pulled out. So it's N out times the area. So I have the time derivative of magnetic field. I don't know what the magnetic field looks like, so I kind of have to stop there. So the rate of change of magnetic field, absolute value. Okay. So this is the voltage out here. And any kind of time dependence, it's inside the magnetic field. So if you are going to get something sinusoidal, the magnetic field will be bearing sinusoidal as a function of time. So, so having figured this part out, so that's what the voltage output is going to be. We look at, all right, so what's the voltage here? And this is the part that will look a little bit backward. Because I'm going to do the same thing here. I have the magnetic field, and I'm going to go through Faraday's law and say, induce the voltage here. Let me write it down. I will end up saying the induced voltage here, the V induced, is equal to, is equal to what I just went through there. So just swapping out some variables, it'll be N in times, we'll say that this area is the same area as the other case. So N in times area times that, the rate of change of the same magnetic field that's going through both of them. So N in times area times the rate of change of the magnetic field. And what we did here made sense. We are trying to get a voltage out from the magnetic field. But why are we doing the same thing here? I thought we are putting voltage in, not taking voltage out. Goes back to the same question that we are handling for the motor. So the question was, when you apply a voltage difference to this loop, how much current do you get out? Right? So, and what we said with this reaction voltage is that the steady state for this is where reaction voltage is equal to the applied battery voltage on some time averaged sense, so that over time the battery is not able to push in any more current than is already there. It's the same idea here. So, it's the question of what is the amount of current when you apply a voltage. Well, if this is an ideal wire, then infinite, because resistance is 0. There's no limit to the current. But it turns out when you apply time-varying current, there is a limit. You don't get to push in infinite amount of current. And the limiting thing is this. The induced voltage is what opposes the applied voltage. And at some kind of steady state is where this induced voltage is equal to the applied voltage, so that no additional current is pushed into the coil or the other way around. Does that make intuitive sense? Yes? Pedro? Makes it, so does it make intuitive sense that this induced voltage over this coil is equal to the input voltage that we are applying? Okay? Yeah. So what this argument is hiding is exactly what's happening with the current, because there's the current is directly related to the magnetic field. So, but the key thing is this. For both V in and V out, this portion is the same. Area of a single loop times the rate of change of magnetic field. It's the same for both of them, which means I can solve both of them for that quantity. So out of this, I can say, all right, A times that So A times rate of change of magnetic field is equal to output voltage divided by N out, V out over N out. And I can do the same thing with this equation. Solve for this. A times rate of change of the magnetic field. I can say that's equal to V in over N in. That's equal to V in over N in. And since this is the same quantity as this, just expressed in different ways, I can say these two are equal to each other. Okay. So this is the transformer relationship, that the voltage in and voltage out, they are very simply related by number of turns. So I can say the ratio of V out over V in is equal to N out over N in. All right, let's see if that's true. So here, according to that, so that's what all this setup is for. Let me, so the way it's going to be set up is I have this function generator set up to something like 1 kilohertz. But the actual frequency, well, it doesn't really matter. So the function generator is, this function generator is set up to produce some frequency of, I don't know if you can see this in the video. Well, this button that's pressed here is the sine wave button. So it's generating sinusoidal wave. That's what you see here. So let's hook this up to my coil that I made. So it's a two set of coils. One set here that has 50 turns. Well, I guess. So the longer set of coils that has 50 turns in it. And the other set on the other side, it has only 10 turns in it. So let me set it up like it's described there. The input voltage into the input coil. Negative here, positive here. And you see the voltage go down a little bit, right? That's the function generator struggling to put through enough current here because it's a low current device. And once again, this is essentially a piece of wire. So, all right, that's fine. So that's our input voltage. It's changed. That's why we keep monitoring it so that we know when it changes. And our output voltage is going to be on the other side here. So, so output voltage here to here. Okay, let me make sure the settings are in the correct setting. So this is 0.5 volts. Let me change to 0.2. So when you look at the setting knob for the voltage here, they are both 0.2 divisions per 0.2 volts per division. So when you read the voltage for channel A, it's 1, 2, 3, 4, 5 divisions. So 1 volt peak to peak. And wait, is that channel A? No, that's channel B. No, that is channel A. Okay, yeah. So channel A produces 1 volt peak to peak, 0.2 times 5 divisions. And this channel B produces, that's about 1 division. So 0.2 volts peak to peak. Is that what you expected based on this formula? Yeah. N out over N in is 10 over 50, 1 over 5. So you expected the output voltage to be 5 times smaller than the input voltage. All right, let's, so when you look at this formula carefully, it doesn't, that thing here requires N out to be smaller than N in. So it could actually be bigger. So I can do that here by turning this connection around. Instead of having the input be applied to the 50 volts, 50 turn wire, I can apply the input to the 10 turn wire. So when I apply the input here, you see the voltage, output voltage go down a lot. So I'm just going to go to higher setting to be able to display it. So and fix the trigger. All right, and let's put in the output, connect the output wires. Then, I have to change this to 50 millivolts. So now you do get so your output voltage, so this is your input voltage, channel A, that's your input voltage, and your output voltage is what just turned on. So you get higher output voltage than the input. Now, when you compare the ratio carefully, you'll see that it's only 1:4 instead of 1:5. So apparently, some of the assumptions we are making didn't work. And the greatest problem is assuming that the magnetic field here is the same magnetic field here. When the loop covers such a small portion, then magnetic field on the other side may not be the same. So this is an example of transformer. So let me, before we go into break, let me end with this question. What did they give up for greater voltage? So you see that we get bigger voltage, but that kind of seems like you're getting something for nothing. So you put in a small amount of voltage, you get a larger voltage. What stops you from building a chain of these transformers and get free energy? Like what stops you from, put another 1:5 transformer, another 1:5 transformer, and get progressively bigger voltages and have a high voltage device that way? What stops you from doing that? Yes?
Ohm's law, current decreases each time.
Current decreases, but not due to Ohm's law. It's another relationship. So it does have to do with energy consideration. So you are never going to get free energy out of this, which means whatever power goes in has to equal power going out. So power going in must be equal to the voltage in times current in. And the power going out here, power going out, is going to be equal to voltage out times the current out. So if you build a step-up transformer that increases voltage, your maximum output current is going to be limited. So sometimes actually people build a step-down transformer for the sole purpose of getting higher current out from a low current device. So that's the thing that has to be at the back of your mind. There's no such thing as a free energy in physics. So you saw that in physics 4A with a simple machine, with the mechanical advantage. The amount of work you do doesn't change. This is the electronic version of that. Amount of power you get out won't change. Yeah. So we've been talking about two of the applications of Faraday's law, and what I want to end with, at least start talking about today, is what usually I used to referring it to as inductance, but your textbook will call it self-inductance, and it's actually reference to the whole mutual inductance that I kind of skipped over. I didn't give you any formulas for mutual inductance, but conceptually we didn't cover it. It's a sort of, if you have some amount of current coming in on one conducting set of wires, then how much voltage gets generated on another set of conducting wires? Not by direct touch, but by inductance, by inductance, by inducing the voltage here through Faraday's law. So self-inductance, which you see a lot more when you're dealing with the circuit, is when this phenomenon where you treated one as in, one as out, happens on the same device. So the model I want to use for this is a solenoid. So imagine that you have a solenoid. Something that looks like this. So imagine that you have a solenoid. Let me try to draw this properly. So you have a solenoid of some number of turns. Let me specify more information than I usually specify on a solenoid. I'm going to say that this, oops, I forgot to, all right. So I'm going to actually give you the length of a solenoid. I call it a solenoid because we are going to use the formulas that we have derived, but I'll give you the actual length of a solenoid. So So I'm not going to be dealing with an infinitely long solenoid. It's an actual solenoid like this one, a physical solenoid, some length, and you say, all right, it has some length and some n number of turns. These are the parameters of this solenoid. And I have to give a couple more parameters. I have to tell you how big the solenoid is. I gave you the length. I have to give you the area. So I have to tell you the cross-sectional area of the solenoid is some area A. Okay? And this is the question. If I put in a current, if I put in some amount of current I, somehow, by some means, and so this current would be, closing the path here, coming back, and flowing that way. So if you apply, if there's some amount of current I flowing, then the question is, what is the voltage difference across the input and output end of the wire? Okay. Let's step over some preliminaries quickly. If this was a constant current, and this is an ideal solenoid, meaning it's made with ideal wires having zero resistance, what would be the voltage difference across the solenoid? Zero, right? Ohm's law says zero voltage develops, and if it's a constant current, then Faraday's law never comes into effect. So yeah, that's what you get in the case. So we are going to explicitly say this current is a time-dependent current. You don't know exactly how time-dependent. It's just a function of time, because that's the only way you are going to get a voltage difference, which may be time-dependent, that's going to be non-zero. Yeah? So I want to come up with an expression for this voltage difference from one end to the other end. So voltage difference from point A to B. Good. All right. So I'm going to use Faraday's law. I will say the voltage difference that develops. So I think this is the most intuitive way I can think about it. Imagine that you have a single loop that you are considering here right now, right? And so that area of the single loop is the area that we are given. What is the, let's see. I want to figure out the direction. I want to, specify the direction so that, so I'm not going to be taking absolute values. I'm going to be actually paying attention to direction this time. And let me say current is drawn, going in as drawn here. And when I drew this current here, this was the direction that was in my head. Let me make it explicit. On this end, it's going to be coming out of the board. On this end, it's going to be going into the board. Good? And then it keeps looping around the same way. So when the current gets here, the current is still coming out of the board and into the board. Okay? So, all right. With that direction of current in mind, let's figure out the direction of magnetic field. What direction is magnetic field inside the solenoid? Downward, all right. I didn't quite think it through, but that's fine. We can deal with the downward magnetic field. All right. So I want to have an expression for magnetic flux through this one loop. So when you try to write down for this one loop, what is the magnetic flux? Guess I will try to use the definition. B dot product with the area vector. Here's the question. Is this product positive or negative? Negative. Why negative? Because magnetic field is downward? Yeah, so this is what you have to figure out here. You have to figure out my area vector. Is my area vector pointing up, or is my area vector pointing down? Because it depends on that, right? So this is where I'm telling you the right-hand rule. So I'm going to pick the direction of my path so that it's the same as the direction of current, so that there's no unnecessary negative sign I have to worry about. So I'm going to always make my path go in the same direction as labeled the direction of current. So if the path is going into the board, out of the board, then the area that it's enclosing, you associate a vector with the right-hand rule so that the normal vector goes in the direction of the thumb. So my area vector, the way it's drawn here, actually points downward. So my B dot A, it's actually positive. So let me write down my flux as, I guess just that's equal to BA. All right, so that's a flux through, this is through a single loop. So what do you think flux is through the entire solenoid? Number of turns, right? With each loop, you get additional flux. You pick up additional flux. So, all right. So for the entire solenoid, so the magnetic flux of the entire solenoid is going to be equal to this times N. So N times BA. All right. So this induced voltage here, delta V is going to be equal to minus, or let me put it this way. The Faraday's law, the original version, E dot dl is going to be minus the rate of change of this solenoid, right? Or flux through the solenoid. Okay. So what I want you to tell me is the direction of the electric field. Let's imagine that the current is increasing. If the current is increasing, what should be the direction of the electric field? So if the current is increasing, then the magnetic field as a function of time is increasing, right? Your magnetic field is increasing. So this derivative d phi b dt, will it be positive or negative? Just this quantity here, the time derivative of the magnetic flux. Positive, because B dot d is getting, from positive value, it's getting more positive. All right, so I multiplied it with the minus sign, which means this whole integral here, this has to be negative, less than 0. All right, in what direction should my induced electric field be? In what direction should my induced electric field be so that this integral ends up being negative? Will it be in the same, so my dl would go in the same direction as the wire. Would my induced electric field go in the same direction or opposite direction? Yeah, opposite direction, right? So my induced electric field goes from, opposite direction. So the induced field will be going into the board here and coming out of the board here. All right, which means as you imagine you are a positive charge. As you go from this end to this end, you are opposing the, so here it's going into the board, out of the board. So as you go through positive charge, as you go through this loop, you are opposing the electric field the whole time, right? So which end has higher voltage, the input end or output end? So let's say I have, a voltage here, V1, and voltage here, V2, which is at higher voltage, V1 or V2. V2 is at higher voltage, right? So what I'm trying to do is I'm trying to imagine closing up this circuit. So let's say I make my V1 be my 0 volt, and this is where I define my reference and everything. Then out, having gone through the loop, so out here you have higher voltage, V2. And when I complete the rest of the circuit, I have to come back down to 0 volt. Good? So what I need to have here is time-dependent voltage source that at the moment the current is flowing this way, so this should be the positive side of the voltage source. This should be the negative side, so that as the charge goes from here to here, it loses voltage and ends up back at the 0 volts. Right? Don't know if I'm making this more confusing than necessary. So what I want you to go through was this, that voltage that's induced through this solenoid, it opposes the voltage that's being applied from outside. But actually, let me come back to this when we do circuits. I think right now, for the purpose of what we are going through, it's forget that we went in this route. We'll use a lot of the expressions, but in terms of the sign, let's worry about that later when we are better prepared to actually deal with the sign. So let me deal with that later. For now, what I want to get at is I want to get at the relationship between current and the voltage that is being induced. So let me put in absolute value signs again. So I have, so this is what I have. The absolute value of the voltage induced. There's a joke that says a good physicist is a physicist that makes only even number of sign errors. And I will tell you that this is one of the areas where it's very common to make sign errors. So voltage induced, or rather absolute value of it is equal to absolute value of minus rate of change of magnetic flux. Right? Let me plug in what I had before. Oops. So this is single loop, which means magnetic flux of a solenoid is equal to the number of loops times BA. So put that in here. So you have absolute value of minus, so I'm going to get rid of the minus sign since it's inside the absolute value. The rate of change of magnetic flux. So when you look at these three quantities, which ones depend on time? Does N depend on time? Does B depend on time? Yeah, B must depend on time because this B, it's the function of current, and current depends on time. So okay, it becomes N times A, time derivative of the magnetic field. Okay? So you have some relationship between induced voltage and the rate of change of magnetic field. And what we do when we define inductance is we take the same model that we had when we are dealing with, so I want to say compared to capacitance. Because inductance will serve a similar role with the magnetic field and current that capacitor did, or capacitance did, with electric charges and electric field. You'll see that later on. So how would you describe the parameters that determine the capacitance of a capacitor?
Surface area.
So that's like the surface area, okay. What else could it determine capacitance? There's no loops in capacitor.
Well, so it's just geometry.
Yeah, so with the things that determine capacitance, it's the geometry and physical constants. So we want to define inductance in a similar way, where inductance only depends on geometry and physical constants. And so what we want to say is that we have some sort of this relationship that with a capacitor, this is what we had, right? Capacitance is equal to charge per voltage. So charge and voltages were dynamic quantities, but capacitor could be, it's a constant depending only on geometric quantities and geometric quantities. We want to have something similar for inductance. So we want to have some ratio of dynamical quantities that results in something that depends only on geometry. When you look at this, we are maybe halfway there. We have one parameter, one dynamical quantity, induced voltage. But on the right-hand side, it's not quite complete yet. Because the magnetic field is not something that you would find in a circuit. It's kind of hard to get at. So I want to express this magnetic field in terms of the current. Good? So I'm going to here, because I'm already out of time, use some of the formulas that we derived earlier. So you guys remember magnetic field of a solenoid, yes? Can someone tell me what the formula for magnetic field of solenoid was from memory? It's not all right done, I haven't memorized. It's mu naught times the loop density, or number of loops per length, times the current. Good? So we are imagining this to be time dependent. It's a function of time, current is the function of time. So when you put this in here, constant, only this will get caught by the time derivative. So we say, all right, so changing this one more time, this is equal to absolute value n times a times mu naught n over L, mu naught n over L times time derivative of current, di dt. So let me box the dynamical quantities in this expression. So let me rewrite this here. So we are saying this is equal to induced voltage. And the dynamical quantities are these, di dt and the induced voltage. So this is the quantity that we want to define as inductance. This is the quantity we want to define as the self or just the inductance. And it's referred to with the letter L. So don't confuse this L with this L. But the common symbol for inductance is L. So taking this as a model, then the way inductance L should be defined is the induced voltage divided by this quantity. So inductance L should be equal to the induced voltage divided by di dt. Okay? And we'll get to this on a future lecture. This is a relationship that's analogous to Ohm's law. And starting next week, actually, we are going to switch back to circuits. We are going to review, DC circuits, and we are finally going to do time-dependent and AC circuits. And this is what we call inductor. This is solenoid is a model of inductor, and the way it behaves in some ways is really similar to resistor. And this is the inductor's version of Ohm's law. And you'll see all of that later. But for today, I just want you to show this quick derivation of inductance. And you'll see more of that when we deal with the circuits. And I will try to do maybe one or two more calculation of inductance. If we don't have time in class, I'll make a video or something. So this was, what I've been saying so far is what we did on Wednesday. I just went through it quickly on Wednesday, so I want you to take a little more time going over it again. Question?
Just a question on that formula you just wrote about inductance.
Yeah.
Is that the
So whenever I say inductance, self is kind of implied because it's either mutual inductance or self-inductance, right? And this is what I mean. Inductor is a bit more important because if we just say inductance without any adjective, we mean self-inductance. We don't mean, when we mean mutual inductance, we'll actually say the word mutual. Yeah, I don't know why a lot of textbooks treat self-inductance as a special case of mutual inductance, but I feel like this is actually more important relationship. Yeah. All right, so yeah. So this is a constant that characterizes this relationship between voltage and current. Okay? And I want you to use this example of inductor to cover one more fairly important physical concept. It's the idea of energy stored in magnetic field. So let me just remind you of what we have talked about before in terms of energy in electrostatics. So, I mean, we don't talk about this enough. I mentioned it last time when we did the capacitor, and I'm bringing it up again so that I can introduce a formula and try to make some sense of it. So let me call this energy in electromagnetism. So the first example is something you have seen before. Imagine I have a parallel plate capacitor. So I have a parallel plate capacitor. Let's say I have some current flowing through this capacitor. There's no actual current flowing through the capacitor, but it looks like it does. Because when you have current coming in, then you have positive charges that are moving into this plate, charging up this plate positively. These positive charges repel the positive charges here. So actually the same amount of current goes out the other side. So even though there's no physical charge jumping across the capacitor, we would still talk about current through the capacitor because it looks like it is from the outside of the black box. So what you have is that as this plate charges up positively, this plate charges up negatively, right? And what we looked at last time is you could look at the energy stored here in terms of look at the energy stored. You can look at it two different ways. You can look at it in terms of voltage. And we took some time deriving this formula for energy stored on the capacitor in terms of voltage. The potential energy stored on the capacitor was 1/2 QV. And you can go back to your notes, figure out where this factor of 1/2 comes from. Right? And another way to look at the amount of energy stored was actually in terms of electric field. Is this sounding familiar? Yes? When you have charge stored on the capacitor, then there's an electric field established within the volume of the capacitor. So there's an electric field here, and what we describe here is the energy density. So the energy density, lowercase u, of this electric field, we derived this expression by considering this example. And the energy density here was 1/2 epsilon naught E squared. Ringing a bell? Yes? So, last time I introduced this, you might have thought, all right, so what are we going to do with this? And this is the reason we introduced it. So in the case of capacitor, you could have easily thought of this in terms of energy in terms of charges. That was easy, and you're done. Like, what else do we need to do? The reason I introduced this at all is so that you would have a point of reference, something to think analogously with when we do magnetism here. Because this is what I want to claim. I want to say, if I have imagine this is a perfect inductor made with perfect wires with zero resistance. If I have some amount of current flowing through here, which means I must have closed the circuit here. If I have some amount of current flowing through here, I'm going to say there is energy stored in this configuration of current flowing through an inductor. That if I have this setup, let me just draw a picture. If I have this setup, an inductor with some amount of current flowing through, I could even call it I naught. If I have some amount of steady current flowing through, then what I'm going to claim is that this setup here, it stores energy. Like, how does the claim make sense? Like, so relying on our intuition about conservative forces and potential energy, it's easier for us to think about how there's stored energy in separated positive and negative charge. Sorry, they look the same. Let me say this is positive charge, this is negative charge. It's easier for us to think, all right, if I have these two charges separated, then there's energy stored here. How do I know that? Well, if I just let go, then these two will attract each other, and this potential energy turns into kinetic energy. That's how I know there's energy stored in this setup. Right? Here, what I'm claiming is that in this arrangement, which has some amount of current flowing through a coil, there's no charge separation, there's no net charge anywhere. I'm saying that this configuration actually has to store some amount of energy. Like, what would you look at intuitively to say, this is why it stores energy? There's, right now, is there a voltage change?
Or it's consistent, right?
Yeah, once I say it's a steady current, then there's no more voltage change, right? So yeah, so this is the part where it's not intuitive. When you look at it, so if we are looking at it right now, I would say, well, right now the voltage difference from this end to this end, delta V, is equal to 0. How do I know that? I connected these 2 points with a piece of wire to complete the circuit. So there's no voltage change there. But I'm still going to say this setup somehow stores energy. Here's one way to think about it. When you imagine this setup and try changing something about this setup, and if you kind of imagine that, that is actually not an easy thing to do. I'm not saying that it's not easy to imagine, although that may be true. What I'm saying is that when you imagine changing something, there are other things you have to change alongside. For example, so right now, there's no actual current flowing through here, but you are just imagining this is some kind of superconductor. So there's some steady current here. Nothing is actually powering the current right now, but it's still flowing. Imagine what happens the moment I try to disconnect this. So the moment this comes off, what happens? Okay, I'm trying to break the circuit, which means I'm trying to make the current go to 0. So now I'm changing the current. The moment I try to change the current here, what happens? Magnetic field is changing. Faraday's law kicks in. So what happens? There's now going to be voltage induced. In fact, you can see this with any electric drill. If you look at the side of or any large motor, if you look at the side of it when you start it, and you usually see when you stop it, you will see a spark. And if you have a large inductor and you suddenly try to disconnect it, you will see at some point you will see a spark jump across it. Because as you try to cut the current, the voltage will build up, and at some point enough voltage will build up to break down the air and form that large spark. So that's one way I know there must be an energy stored here, because I'm pretty sure it takes energy to produce that spark. And well, there's no power supply. The only thing that was there was this current that was flowing. So, but once again, it's not intuitive. So it's not intuitive exactly how that energy is there. So it's not easy to see. Well, for example, if we store energy, I guess this is the question that we ought to be able to answer. How much energy is there? So we can make the intuitive argument that there's some energy there, because the moment we try to break the circuit, we see that energy released. But the question now we want to ask is, okay, how much energy is stored there? How would you calculate it? So Faraday's law would be difficult. So because you're trying to calculate how much energy is stored here while the current is not changing. Because you're trying to calculate how much energy is stored in the state where there's no voltage change. But actually, you can use Faraday's law. Let me give you a way to intuitively calculate how much energy using Faraday's law. So what I have to do here is it's much the similar way with how we did it for capacitor. We have to imagine a particular physical setup which will allow us to calculate, okay, this much energy was needed to put this much current through here. So I'm going to say, well, so that's how much energy is stored here, because I'm idealizing everything so that there's no energy dissipation anywhere. So this is what I'm going to, the setup that I'm going to imagine. Let's say I'm starting out with a 0 current, so that at least very initially, there's a 0 energy stored there. So what I'm going to say is I'm going to hook this up to a power supply, but it's a very special kind of power supply. This is a very special kind of power supply. It's almost too special to be impractical, but I will describe it anyway. You are never going to see this actually physically. So it's a very carefully controlled power supply, which this time varying thing that it provides, this is actually current. This is the current as a function of time. And the way it's providing this time varying current is it does that by applying a steady, constant voltage of V0. So I realized that when I was looking at this expression. So I want this expression to be simple, right? So what I want my current to be is I want it to be expressed as a function of time. So it's going to some maximum value I0 at some final time. But as a function of time, it'll look like I0 over the total duration of time, capital T, times the lowercase t, time at some particular moment. So when it reaches this time t, then this power supply will simply maintain this voltage I0. And so when it simply maintains that voltage I0, the voltage will actually drop to 0, because it'll find that it doesn't have to put in any effort to keep the current going. And the same thing here. So it goes from 0 voltage. And as it's trying to increase the current, it has to apply a steady, constant voltage. And once the current is no longer changing, then the voltage it applies drops to 0. Yep. Everyone good? Yes?
The uppercase T underneath, is that period or something?
Yeah, well, it's a time constant. You could call it period. It's that uppercase T. So if you're looking at this mini graph that I'm drawing as the function of time and voltage and current, then that uppercase T would be represented here as this duration of time. This is T. Okay? So what I'm going to look at is how much power does this power supply have to put into this solenoid? And that's how much energy would end up being stored here. Okay? So how do I calculate how much power is being input? How do I calculate the input power? Any ideas? Like, what expression support for power do you know that would be useful here? Actually, what expression for power do you remember? There should be 3 formulas which are useful at different times, but you should have all 3 memorized. That applies to electricity and magnetism, or rather electric circuit. People don't remember this? Yeah, so that's the very basic relationship that both Sandia and Katie were saying. Power in electric circumstances, it's given by current times voltage. And you can write out the current to see that this is the rate of change of energy. And actually, we can just stop here. This is going to be the formula that I use. If you have resistors in the circuit, then the other 2 formulas like I squared R and V squared over R may be useful. But this particular setup is a concocted artificial setup where resistance is specifically 0. Okay? So we are going to use this basic relationship for electric power. So power in must be equal to the voltage in times the current in. Right? Now here, I don't want power. That's the power is the rate of change of energy. I don't want that. I actually want the total change in energy. Yes? So from here, how do I calculate the total change in energy? From here, how do I calculate the total change in total energy in? Yeah, why do you say integral, Sangmin? Because you're, okay. So, yeah, if you jump to there, so can you tell me how you do set up the integral? Yeah, this is why I don't want people to just jump to the integral. So integral is something you set up once you realize the simple algebra wouldn't work. I really want you guys to get out of the habit of simply saying integral. Because as I said a couple times before, that's like, someone asks you, how do you calculate resistance here? And you say multiply or divide. It's just a mathematical procedure. You have to know conceptually what's behind that integral you are setting up. So, I mean, if you are looking at what I've written down so far, that knowing that power is rate of change of energy, if you want total change in energy, how would you calculate power? Yeah, so sorry, how would you calculate energy? You would do power times the duration of time, right? So this should be your intuitive first answer. That change of energy in, or total amount of energy that goes in, is the amount of power in times the amount of time that it takes. So this is your starting intuitive conceptual expression. Now, having written this down, you should realize soon that if I simply do multiplication here, it doesn't work. Why does it not work? Yeah, current in is dependent on time. So this is, imagine actually doing this calculation. Imagine you want the actual numerical value of energy. So you plug in the numerical value of power, numerical value of duration of time. You know the duration of time, t, but this is where you run into a problem. So the current is a function of time, which means, so current in is a function of time, which means this time power in is also a function of time. So depending on which time you are looking at, your power in could be 0, with a 0 amount of current flowing, or your power in could be at some maximum value. But your amount of power you are putting in, it's a function of time. It's changing with the time. So there's no one value of time power that you can plug in. So what do you do in that case? Yeah. You imagine now breaking this up into very small time intervals. You imagine breaking this up so that, all right, we cannot deal with the entire duration of time all at once. But what we can do is we can deal with a tiny amount of time interval. For the tiny amount of time interval, I can say my power in is more or less a constant rate. I can say, okay, so that's the tiny amount of change of energy. And so this is your starting place for setting up the integral. That's why I don't want you to say integral right at the beginning, because for 9 out of 10 of you who say that, you won't know how to set up the integral. But more than half of you who start out with the algebraic relationship that I wrote down, you'll be able to see how that algebraic relationship turns into your integrand. Okay, so let me write this down. So amount of power that goes in, so the total energy in is going to be, so based on this, it's going to be the integral over the total duration of time from time equals 0 to the end time capital T of the little change per each small interval of time. So that's equal to, I think I can actually do this on this small space. So power in is the voltage V naught times the current. So it'll be V naught I naught divided by T times T dt. Good. All right, are all my units right? Yeah, I think my units are right. So do the integral. It's a simple integral, polynomial integral. So, integral is, the antiderivative is 1/2 t squared. So this is V naught I naught over capital T, 1/2 t squared, evaluated from 0 to capital T. Plug in this capital T. One factor of it cancels, and you get energy in is equal to V naught I naught over 2 times the duration of time t. Oh, I guess I could have done that without an integral. I'm multiplying this constant function times this triangular thing. So it's the area of the triangle of the, but whatever. So that's the amount of energy that went in. So what I want to say is that this energy that went in is equal to the amount of energy that's stored in this, that's amount of energy that's stored in this solenoid. So this is the statement I want to make. So this is the statement I want to make, that amount of energy that went in is equal to energy stored in solenoid. So the amount of energy stored in solenoid is equal to V naught times I naught over 2 times T. This expression is a little bit, I don't know, unsatisfactory. So here's the main reason that it's not really satisfactory to me, at least. So how did I start describing this solenoid? Let me redraw the solenoid I was describing earlier. The solenoid that I started describing wasn't exactly like this complicated setup. It was a general solenoid. It was, any kind of coil where I said there was a constant current that's flowing through here, right? Was there anything like this voltage V naught in this picture? No, right? So the expression that we came up with, it's very specific to how you charged up the solenoid. So, this expression is true for this, but if I want a generally applicable expression, then this doesn't work. Because if I'm simply telling you, well, I have a solenoid, I charge it up to I naught, then you sort of want to be able to say how much energy is stored here. Really, as a function of this current I naught. You don't want to involve any, voltage that you don't know how it was actually applied, right? So what I'm going to try to do is I'm going to try to rewrite this expression so that it's independent of this voltage. So for that I go back to this relationship here. So let me rewrite this expression over there. So what I have is, all right, the voltage across the inductor, voltage change across the inductor is equal to the inductance times rate of change of current, right? So let me actually do this in a different color because I don't want this getting confused with the generally applicable expressions. I mean, this is what I wrote down right now is generally applicable, but I'm going to plug in a specific situation. So this voltage change across inductor is inductance times the rate of change of current. So, well, the voltage that I applied was V naught, right? There was a constant voltage I applied. So V naught is equal to inductance times the rate of change of current. And the way I characterized it is here. As a result of this constant voltage being applied, I had this current as a function of time that had a constant rate of change. And the constant rate of change was I naught divided by capital T. So that this constant rate of change was I naught divided by capital T. So for this specific situation, this is the relationship that I can use to try to get rid of V naught here. So let me plug that in and let's see what happens. So plugging this in, I get, well, I guess I should just plug it in. L I naught over T times the remaining quantities, I naught T over 2. And you see that some of the things cancel out. That's kind of convenient. The thing that was making me hesitate for a while back, if you noticed it, was that I had this time T that I didn't want in my final expression either, because that's sort of arbitrary thing. Here, you see that it cancels out. So that in my final generally applicable expression, it doesn't depend on that amount of time either. It doesn't matter if it takes me a minute to charge the inductor or a year to charge the inductor. So with that, if I write out this expression, it becomes 1/2 L I naught squared. And when you look at this, I want you to be reminded of what you saw with capacitor. Because with the capacitor, this is what we had before. So this was the expression for energy stored. And using the definition of capacitance, we could actually rewrite this in two different ways, right? Using, Q is equal to CV, we could rewrite this as 1/2 CV squared, or we could rewrite this as 1/2 Q squared over C. Notice this dynamic quantity squared. And in fact, this Q times V is still dynamic quantity squared because both Q and V are dynamic. And here, I have the dynamic quantity current squared. That's somehow being a common feature. Yeah? And let me wrap up this discussion with this last derivation of a formula. So you can actually end this discussion here, and there will be nothing wrong with it. You could say this expression is the formula for energy stored in inductor. Because, well, everything here seems reasonable. As in, if I have an inductor, I know everything there is to know about it, then I would know its inductance. And I know the current, so I know it's the current that somehow stores energy in it. So everything seems fine. I don't really have to do anything more there. But I want to take this, take a last step that will, once again, I hope remind you of this last step we did here. Because once again, it's intuitive to imagine how energy is stored in a charge. It's far less intuitive to imagine how is energy being stored in a current. Like current is just charge moving. So once I bring it to that one last step, the similarity between this picture that you saw before and the similarity here will become greater. So let me do this one last step. So do people remember how we went from this step to this step here? Yes? No? If you don't, that's fine. The way I think I did it was I started out with this and plugged in an expression for C, for the parallel capacitor. And then we gave some interpretation to some grouping of terms. I am going to do the same thing here. I have been very careful not to erase this inductance of a solenoid so that I can plug it in and see if I can make any sense of the resulting relationship. So the inductance of a solenoid is, so all this, plugging that in, it's equal to 1/2 mu naught n squared A over L times I naught squared. That doesn't feel like there's anything profound here. One thing I remember I had to do here was I had to rewrite voltage in terms of electric field, because electric field is the fundamental quantity I was trying to get at. So I'm going to try to do the same thing here. So I have this relationship between the current and the magnetic field. So I'm going to try to say, all right, let's solve this for the current and plug it in there. Try to get everything in terms of magnetic field instead of current. Let's see what happens. So solving this for current, I naught, it's going to be the magnetic field, B naught, times L. Sorry, I forgot to change this to lowercase l. Divided by mu naught n. Right? Let me plug this in there and let's see what happens. So this is equal to 1/2 mu naught n squared A over L times all of that squared. So B naught L squared over mu naught n squared. Oops, sorry. Sorry, I have to square each one of these. Good. This is the current squared. Everyone good? Okay, so let me cancel out some things that cancel out. There are things that cancel out right from the start. The one factor of length cancels this one factor of length. Number of loops cancel. So it doesn't matter how many loops are there. I mean, a factor inductance, but in the final expression, the number of loops doesn't matter. That's, I don't know, surprising to me. So mu naught kind of, one factor of mu naught cancels out this one factor there. So this is what I see. Let me write down the cleaned up version. The cleaned up version is 1/2. Let me group the terms in two groups. The first group that I want to write down is 1/2 mu naught, 1/2 mu naught times magnetic field squared. That's the first group of terms. The second group of terms are everything that remains. Area times the length. So A times L. What is this quantity? What kind of meaning would you assign to that combination of quantity in the second group? Volume, right? Area of the cylinder times the height of the cylinder. So this is the volume inside solenoid. So knowing the left-hand side, that's the energy stored in solenoid. And some quantity times the volume is giving you energy stored in solenoid, what kind of meaning would you assign to this? Yeah, energy density. Because it's, energy is equal to volume times this constant quantity. This is the energy density. So this is the, we call this energy density of magnetic field. And when you now compare it to this expression, you see the similarity here. They have this inexplicable factor of 1/2 that really comes from an integral that we did at some point along the line. And they both are square in terms of the field. And there's some coefficient here. Now that's the part that you can really explain. Why is the epsilon not in the numerator and mu not in the denominator? That you just have to remember. So this is the energy density of magnetic field. And this is the reason so that we can go over this now, is the reason we took time to go over this when we did the static electricity. So that you would have something to refer back to and see that the energy being stored in a current that's flowing through solenoid in some very abstract, weird way is similar to energy being stored on a plate of plates that are carrying charges. Hi, this is example calculation for a toroid inductor. So I should start out with a description of a toroid. In case you haven't seen it before, this is what a toroid looks like. So a toroid would have a cross section. So it can have any cross section, but for this example, I'm going to imagine a toroid with a rectangular cross section. This is the sketch of the rectangular cross section. And the way to make a toroid would be to revolve it around an axis. So revolve around an axis, vertical axis here. So this is a toroid. And when we talk about toroid, this is the three-dimensional object that I want you to visualize. And for the inductor or inductance calculation, you have to imagine a wire that's wrapped around this toroid in the way that I'm just going to draw right now. So for our example calculation, imagine a toroid with a rectangular cross section that you just saw before. Let me finish this sketch with the full perspective drawing of this three-dimensional object. This is the inner diameter, and this is the outer diameter. There's the same cross section on the right-hand side as there was in the left-hand side. Let me give me some parameters of this toroid. So the toroid has a height, h, and let me specify the width this way. I'll give the inner radius R1 and the outer radius R2. And to finish specifying the toroid, I have to tell you how the wire is wrapped around this geometric object. So this is how the wire is wrapped around. Let me draw a few representative wires. So let's say starting from here, it goes radially outward and then wraps downward. Along the bottom surface, it wraps back and comes up along the inner diameter, comes out radially again, wraps down, and then goes back along the bottom surface, comes back up, and then comes out, and so on. It's gonna get quite tedious drawing all of this. So you have to imagine this wrapping around to continue around the entire toroid. So I won't draw the whole thing here. So this is the perspective view. Let me draw one more view that'll help us describe this toroid more accurately. That would be the top view. That is, going back to the toroid that we drew before, imagine that we are looking at the top surface here. So this is the top view of the toroid. So these two circles represent the inner and outer radius of the toroid. Let me draw something to illustrate the wires. So here I have drawn 29 circles representing 29 wires coming out of the board. Let me draw the symbols for that, wires coming out of the board. But of course, these don't have to be 29. It can be really n number of wires. So n, capital N, represents the number of times the wires wrapped around. Let me finish drawing this representation of the wires in the top view. Alright, excuse my drawing, and imagine that these are uniformly wrapped around. So the wire comes out of the board, radially goes out, and on the outside radius, it goes into the board again. And I'm not drawing here the return wire on the other side, along the bottom of the toroid. Okay, let me finish the drawing here. I have to indicate the direction of the wire. Well, I don't have to, I want to. All going into the board. Alright. So this is the question we are trying to answer in this example calculation. What is the inductance? So let's just start out with the definition. This is how inductance was defined as we covered Faraday's law and inductors. The way inductance L is defined is through this defining relationship, that the induced voltage is equal to the inductance L times rate of change of current. This the voltage, remember, is going to come from Faraday's law, which says that the induced voltage is equal to minus rate of change of the magnetic flux. So what that means is we are going to need the magnetic field to calculate the magnetic flux. So this is a good example calculation because it has many parts. To complete this calculation from beginning to end requires that you really understand everything about magnetism thoroughly. That's why I want you to show this calculation to you in detail, in video format, so that you can watch it on your own time, rewatch any of the parts you need to, or skip the parts that you feel like you understand it pretty well. So I'm going to break up this problem into two parts. The first part is where we are going to calculate the magnetic field. So we'll calculate the magnetic field as a function of distance from the center of the toroid, and this will be an Ampere's law question. If you feel like you understood that part well when we went through it, then you can skip ahead to the part where we've already found the magnetic field. Now we are using that to try to calculate the inductance. If you feel like you need a review of application of Ampere's law, then please watch on. And the second part of the question is that once we have an expression for the magnetic field, then we are going to calculate the magnetic flux, which can be expressed as the area integral of B dot dA. And you'll find that once we find the magnetic flux, then it's an easy step from there to finish up this portion of Faraday's law, to say that the rate of change of magnetic flux is equal to induced voltage, and see if we can factor out di dt and call the remaining constant term the inductance. All right, so let's sketch out the steps for doing part 1, finding out the magnetic field. So we have to use Ampere's law, meaning we have to look at this geometry and exploit any symmetry that we see to help us find the magnetic field, magnitude of magnetic field, from the Ampere's law. Let me remind you what Ampere's law says. Ampere's law says that the line integral of magnetic field B dot dl around the closed loop is equal to mu naught times the amount of current enclosed. So just like with application of Gauss's law, you need to have a sense of the direction of magnetic field and the symmetry that you can use so that you can, one, work out this dot product here, and two, so that you can come up with an Amperian loop, a path along which you will calculate this line integral, where from your sense of the direction of magnetic field, you can say what the dot product is. Normally you want the direction between B and DL to be either 90 degrees or 0 degrees, so that this dot product works out nicely. And you want to be able to use a symmetry argument to say that the magnitude of magnetic field isn't changing, so you can pull it outside the integral and you can complete the rest without actually knowing what the field is. So, alright, so let's just start out with the one, direction of the magnetic field. So we look at this toroid and we are going to think about the direction of magnetic field inside all these loops that are wrapping around the toroid. So this is where it's useful to have a sense of direction for the magnetic field due to a loop of current. Let me imagine this loop here that's lying along the the plane of the board. So using my right hand, this is the version of the shortcut rule I'm using. I'm using the shortcut rule for the loop of current, and I orient my right hand so that my fingers curl around in the direction of the loop. Then as my fingers curl around in the direction of the loop, left to right on the bottom, up along the inner diameter, and then right to left along the top, then the direction of my thumb points in the direction of the magnetic field that's generated by that loop of current. So for this loop outlined here, the right hand rule says that the magnetic field is coming out of the board. Magnetic field is coming out of the board here, going into the board here. So let me draw just one loop for representation of the magnetic field in the top view. Magnetic field will go along this circular field line. Imagine it's a perfect circle. On the left side, it'll be coming towards me out of the plane, and then on the right side, it'll be going away from me into the plane. So that's the magnetic field line, and I drew just one circle, but if you drew more complete field line, then it'll be a series of concentric circles. Now, toroid geometry has really one symmetry here, and the symmetry is the rotational symmetry. As you take the toroid, and when you rotate it about the center of the toroid, or more precisely about an axis that's going through the center, let's say out of the plane, or into the plane, doesn't matter, it's an axis. So as you rotate this toroid about that axis, nothing changes. If you imagine it's uniformly wrapped around, excuse my drawing again, then if you rotate it 90 degrees, or if you rotate it by any amount of angle, then nothing in the toroid changes. What that means, we can make this argument. So given this circle of radius r, let me use the letter capital R. Given this circle of radius r, we can say that the magnetic field can be expressed as a function of this radius r alone. No dependence on angle because of this rotational symmetry. If you have magnetic field at this point, the magnitude of the magnetic field should be the same all the way around this circle, because you can rotate this geometry by any amount of angle, and nothing would change. So that's our setup. Now, understanding all of that, to finally apply Ampere's law, we have to define an Amperian loop. It's going to be a path that exploits all this symmetry that has been pointed out. So let me pick this circular path. So let's say we want to find the magnetic field at this point, which is at a distance r from the center of the toroid. Then what we would do is we would define our Amperian loop as a circle that goes through this point. So it would look something like this. And we need to assign a sense of direction. Let's say if we are looking at dl at this point here, let's say it goes along the same direction as the direction of the magnetic field. Then our expressions have no unnecessary negative sign. So with this Amperian loop that I defined, this is what we can say about Ampere's law. We can say that the left-hand side becomes the line integral of B dot dl, but magnetic field B and the path element dl, they go in the same direction. So this dot product simply becomes the magnitude B times the length of path element dl. So in addition, so since this path is a circular path, we can say that based on the rotational symmetry we pointed out, that the magnitude of magnetic field is actually constant along that path. So we can pull the magnetic field outside of the integral. And we can say this is equal to magnetic field times the line integral dl. But this is a very simple expression. That's simply the path length of the circle. Feel like I know circumference of a circle. So this should be equal to the magnetic field strength times the circumference of the circle of radius r, 2 pi r. Now, based on Ampere's law, this should be equal to the constant mu naught times current enclosed. And this current enclosed deserves a little bit more thought than usual. So by current enclosed, we mean how much current is poking through the area that is bounded by the Amperian loop. Well, these are the currents that are poking through that area bounded by Ampere's loop. So each wire carries current I, so that means there's N times I amount of current enclosed. So the right hand side is equal to mu naught N I. Alright, let's solve this for magnetic field. So magnetic field is, as a function of radius r, equal to mu naught N I divided by 2 pi r. If this reminds you of the formula for the magnetic field that you derived for line current, that's fine. It actually is pretty similar. The only difference is that there's this N. I don't know if I would draw any deeper connection beyond that, but it looks similar, and all the steps we did are correct. So, all right, so we found the magnetic field as a function of r. Now, one thing I do want to note is that it is a function of r. It's not uniform magnetic field over this cross-sectional area. And that's the part that's going to make our next calculation a little bit more complicated. So, well, let's move on. All right, we found the magnetic field inside the toroid, and that is equal to mu naught N I divided by 2 pi r. So this r, it has a range. The minimum radius r is r1. Less than that, you're outside the toroid, so all the calculation is different. and the maximum radius is outside radius, R2. Outside of that, once again, the enclosed current becomes very different. So we remain within these bounds to be inside the toroid. So for the second step, in trying to find the inductance of this inductor, is we have to come up with an analytical expression for the magnetic flux. Now, with the solenoid example, we simply said that magnetic flux is equal to magnetic field times area. That does not work here. That's because the magnetic field depends on the distance from the center of the toroid. So this old expression does not work. We have to fall back on the integral-based definition of magnetic flux, that the small contribution to magnetic flux is the magnetic field times the area element, dA, and we have to integrate this over the surface that we are considering. In our case, I want you to imagine this surface here, the cross-sectional area, the rectangular surface here. So, all right, I guess let's write it out. So the magnetic field is coming out of the board here. Let's say dA also comes out of the board. So this B dot dA would be simply B dA. Now, it's an area integral, so it's going to involve a double integral here. Let's try to parameterize this integral in a convenient way. I think the most convenient way to do it would be using this axis here along the x direction and y direction. So the integral would be in terms of the area element, dx, dy. And we have to specify the integral. The x integral goes from x is equal to r1, the inner radius, to x is equal to r2, the outer radius. And the y integral would go from y is equal to 0, let's say that's at the bottom of the toroid, to the full height of h. All right, so that's the integral there. And our magnetic field would be a function of x, because x represents the distance from the center of the toroid out to whichever point we are looking at. Okay, so let's write it out. This is equal to the magnetic field in terms of x, mu naught Ni over 2 pi x, integrated in terms of x and y, with the x going from r1 to r2 and the y going from 0 to h. Seems like an easy enough integral. Notice that nothing here actually depends on y. So the y integral simply becomes multiplication by h. Now, there's something that does depend on x. It's 1 over x. So the antiderivative will be natural log. So let me write this out. So factoring out all the constants and doing the dy integral, it's equal to mu naught times Ni over 2 pi times the h that's coming from the y integral. And I'm now writing down the integral for 1 over x integrated with respect to x. So that would be the natural log of x evaluated from x equals r1 to r2. So writing it all out, this becomes mu naught and I h over 2 pi times natural log of r2 over r1. I skipped one step involving the logarithm algebra. So the step I skipped is writing down natural log of R2 minus natural log of R1. Doing logarithm algebra, that becomes natural log of R2 over R1. All right. Now, when you look at this carefully, I hope you realize that we are missing something here. It's really a common mistake to make. I make this all the time. So this magnetic flux that we just calculated is magnetic flux through a single loop. It's magnetic flux through a single loop here. So let me write that out before I forget. So this is magnetic flux through a single loop. This toroid has n loops total. And each time this wire wraps around, there's this much magnetic flux going through the additional loop. So when there's n loop, the total magnetic flux will be this single loop magnetic flux times n. So the total magnetic flux is mu naught times n squared, and the rest of the expression. All right, that's the magnetic flux. It does require careful calculation, but it's not that complicated. It's doable. That's why I like this illustration, because it's not, simple, trivial expression that you might guess. It does take work, but it's a doable work. So now we are going to use this expression for magnetic flux to figure out an expression for induced voltage, and from that calculate the inductance of this toroid. All right, so we have the magnetic flux. This is the total magnetic flux, as you can see in this n squared. So the induced voltage around the whole toroid, imagine all those n loops, will be equal to minus rate of change of magnetic flux. But for the purpose of the calculation of inductance, let me not worry about all these minus signs. So I'll just say I only care about the magnitude. I'm not going to worry about the minus sign. So let me take the time derivative here. When you look at the expression for the magnetic flux, it looks like everything here is constant with respect to time, except for possibly one. The current might be a function of time. So let me write this out. All the constants times the rate of change of current. So this is the form of the expression that we are looking for. So this boxed term here is the inductance of the toroid. And you can see here that nothing here depends on any dynamic quantity. That it depends on the physical constant and the geometric parameters. Oops, speaking of geometric parameters, I forgot about this height h. Let me put it in here. This thing times h. I copied it wrong. All right, so let me write down what the inductance of toroid is. So remember all these parameters that we use to specify the toroid. The inner and the outer radius, height of the toroid, and the number of turns n. So in terms of all those quantities, the inductance of toroid is given by mu naught n squared times h times natural log of R2 over R1 divided by 2 pi. So that's it. That's the example calculation for inductance of toroid. There can be more complicated geometries, but in this class we won't really worry about them. All the models of toroid that you might possibly deal with in this lower division electromagnetic class is the solenoid. You have seen that calculation. It's a lot simpler. And the toroid. This is really as complicated as inductance calculation is going to get. All right, so that's everything I have. Until next time, bye.